is the minimum velocity or minimum speed with which a particle must be or object must be projected from the surface of the earth so that it will escape out of the planet. Not only earth, any planet. Each and every planet has its own escape velocity. We have to derive the expression for it. Let us consider an object which is on the surface of earth. It has been projected to certain height where its velocity will become 0, final velocity will become 0, and then its potential energy will also become 0. By applying law of conservation of energy, we can calculate the escape speed in this particular case. At the initial position, we can say the kinetic energy is half m v escape square, because this is the velocity with which the object has been projected from the surface of earth. Potential energy is minus of g me m divided by re, where r is the radius of the earth from where it has been projected. This is the initial energy, total initial energy. Final energy can be represented as half mv square. Some velocity will be there at some point. Minus of g me m divided by re plus h. Actually, this is the potential energy of the same object at some height h. If it is for the maximum condition or the minimum, for the minimum speed with which the object must be projected from the surface of earth, then we can say here at the final stage, as the object reaches this particular point, then we can say its velocity will become 0. Right at the same time, it moves out of, it is considered that it moves out of or it has reached the point infinity where its potential will become 0. So potential energy will be 0 at this particular point. By assuming these two cases in mind, gravitational or kinetic energy is taken to be 0, potential energy is also taken to be 0 at the final case. Then we can say, according to law of conservation of energy, this has been written, from which we can write half m v escape square is equal to g me m divided by re. M cancels out. V escape is equal to square root of 2 g me divided by re. Or otherwise I can write 2 g re. This is the expression for escape velocity. V escape is equal to square root of 2 g me divided by re or square root of 2 g re. This is for the condition where the kinetic energy becomes 0 and the potential energy becomes 0 at a particular point. Suppose in the midway, if the object is said to be moving under projection, then we cannot say its kinetic energy and the potential energy are 0. So in such a case, according to law of conservation of energy, you have to take this formula, half m v escape square minus of g me m divided by re equals half m v square minus of g me m divided by re plus h. When the object is projected upwards and it is under flight, right? This is the minimum condition actually. This is for the minimum condition. V escape is equal to square root of 2 g me divided by r. Minimum condition in the sense the minimum velocity with which the object must be projected from the surface of earth. This is for earth. For any planet in general, we have to write it as square root of 2 gm divided by r or square root of 2 gr, where g is the small g is the value of acceleration due to gravity of the respective planet and r is the radius of the planet, from which we can calculate the escape velocity. As you know, the escape speed of earth is 11.2 km per second. Right? 11 per second. Fine. This is about the escape speed. Now to speak about the escape speed. If you speak about the escape speed of black holes, what will be the case? The escape speed of black holes is equal to c, is equal to square root of 2 gm divided by r, where m is the mass of black hole, r is the radius of black hole, and this is equivalent to c. In the sense, you must project any object with a velocity equivalent to velocity of light. Then only the object will be escape out of the black hole. So we can simply say here, from a black hole, nothing can escape. From a black hole, nothing can escape. So c equals square root of 2 gm divided by r, or otherwise square root of 2 gr. Square root of 2 gr. Where the g and R are entirely different. You should not substitute the values of the value of acceleration due to gravity of Earth and the radius of Earth. Here it is the value of acceleration due to gravity on black hole and then radius of the black hole. Right? This is about the escape velocity of black hole. There are certain important points which are related to the escape speed. What are they? Escape speed is independent of the mass that is projected and also the angle with which it has been projected. So direction of projection is not a matter of fact. Mass of the object that has been projected is also not a matter of fact. Whatever the masses, its escape speed is 11.2 kilometer per second in case of Earth. Right? Whether you are throwing a small stone or a satellite or a very big object, the velocity must be 11.2 km per second. So it is independent of mass of the object that has been thrown upwards. Also, it is independent of the projection. They will ask you a question. If an object is projected at an angle of 60 degrees with respect to the surface of Earth, what will be the value of escape speed? Same, 11.2 km per second, because it is independent of the direction of projection even. Also, we know the expression for RMS speed. Vrms equals 3RT divided by m. 3RT divided by m. This is the RMS speed of gas molecules. If the escape speed of the gas molecules or the RMS speed of gas molecules is greater than the escape speed, I can write Vrms is greater than the escape speed, no molecule will stay on the surface of on the atmosphere of the planet. It will escape out of the planet, leaving no atmosphere to the planet. On the surface of Earth, we can say the value of escape speed is more than RMS speed. So no molecule will escape out of the atmosphere of planet Earth. So Earth has an atmosphere. Suppose in the case of Moon, this is for Earth. In case of Moon, what will be the condition? The escape speed is less than the RMS speed. The RMS speed of the gas molecules is much more when compared to the escape speed. So all the molecules will move away from the atmosphere of Moon, leaving no atmosphere to Moon. Right? This is about the escape speed of the planets. If an object is thrown with a velocity v, which is greater than v, then what will happen? The object will move into interstellar space with a velocity which is equal to v square minus of v square. V square minus of v square. Suppose if you are projecting the same object with a velocity v less than v, then the object will move up to a particular height and it will stay at the height and fall down once again, or otherwise it will move with some orbital velocity, starts to revolve around the Earth in these two cases. So if v is greater than v, it will move into the interstellar space where v equals square root of v square minus of v square. If v is less than v, then what will happen? The object will reach a particular height and will return back, or otherwise it will start revolve around the Earth's surface, revolve around the Earth. Right. Laws of planetary motion. There are three laws. One is law of orbits, second one law of areas, and third one law of periods. Law of orbit states that the line joining the sun and the planet sweeps out equal areas law of orbits states that each planet revolves around the sun in elliptical orbit with sun at one of its foci. Law of areas states that the line joining the sun and the planet sweeps out equal areas in equal intervals of time. The aerial vector is a constant in this case, which is due to the conservation of angular momentum in this particular case. Law of areas, in case of law of areas, which one is conserved? The question will be asked like this: which one is conserved? Which are the following physical quantities conserved in law of areas? Angular momentum is conserved. Angular momentum is conserved. Aerial vector is nothing but dA by dr. Aerial vector is nothing but dA by dr. This dA by dr when solved will give you the angular momentum conservation. For example, if you consider the elliptical motion of the planet, Sun is at the center, you can say V is the velocity with which the planet is moving, and it reaches from A to B. It takes a time dt. So the distance traveled is V into dt. This is the area swept by the radius vector. Let us mark this as R. Then we know very well the area of this particular triangle is a half BH. This is half into breadth is V dt. H is R. So area can be represented as half V dt into R. This dA by dr can be represented as d by dr of half V dt into R. Or as dA by dt. Sorry, dA by dt. So V into R divided by 2 into dt divided by dt. So this is half VR. If you multiply and divide by m, you will have mvr divided by 2m. mvr is angular momentum, which is L divided by 2m. So dA by dt is nothing but a constant, area vector. Rate of the angle swept by the radius vector, or the line joining the sun and the planet, sweeps out equal areas in equal intervals of time. So this dA by dt, if the change in area with respect to change in time is always a constant. How it is coming as a constant is based on this value of L. So if dA by dt is constant, then this L by 2m, L is also a constant. Angular momentum is conserved in this case. This is second law of Kepler, law of areas. Law of periods is simple. Planet is revolving around the sun in elliptical orbits. Let us say the perigee position is at a distance r1, apogee position is at a distance r2. This is the semi-major axis A and semi-minor axis is B. Then we can write the square of the period of revolution of the planet around the sun is directly proportional to the cube of the mean distance of the planet from the sun. Cube of the mean distance of the planet from the sun. Either you can say cube of the mean distance of the planet from the sun or cube of the semi-major axis of the planet from the sun. This can also be expressed as t square is proportional to r1 plus r2 by 2 the whole cube. R1 plus R2 by 2 the whole cube. This is another way of expressing the Kepler's third law of planetary motion, which we call law of periods. Right? Of a second. Let us consider the Earth having mass me. Its radius is Re. At a particular 8h from the surface of Earth, the satellite is undergoing a circular motion. This is Re. The total height can be taken as small r. We have to calculate the orbital velocity. Satellite is said to have a mass m. It's moving with a velocity v naught tangentially along the circular orbit. The necessary centripetal force power for this mass m of the satellite is provided by the gravitational force of attraction between the Earth and the satellite. The centripetal force is mv naught square divided by r is equal to g me m divided by r square. This m can be cancelled, r can be cancelled. Vo is equal to square root of g me divided by r. G me divided by r. This is the expression for orbital velocity. Also, we can write g me divided by re plus h, since r equals h. Small r is equal to re plus h. If h is very much less than re, if h is very much less than re, we can neglect h, so that Vo will be equal to square root of g me divided by r. G me divided by r. This is equivalent to square root of g r. gr. Orbital velocity and escape velocity can be related here. As escape velocity, V escape is equal to square root of 2gre and orbital velocity is square root of gre. We can compare escape velocity with orbital velocity as V escape is equal to square root 2 times that of V orbital velocity. So escape velocity is root 2 times that of orbital velocity. Which one is greater? Escape velocity is greater than orbital velocity. Right? This is the relation connecting escape velocity and orbital velocity. When you are asked to calculate the orbital velocity, whose heights are comparable to the radius of the Earth, then you have to go on with this expression. If the heights are close to the surface of Earth, then you can go directly with VO equals square root of gr. Right? Now, we can speak about the time period of revolution of the satellite around the Earth. Time period of satellite around the Earth can be given as T equals 2 pi r divided by VO. This is 2 pi r divided by VO equals square root of GME divided by R. GME divided by R. I can write this as 2 pi r divided by root of GME into r power 1 by 2. So this will become 2 pi r power 3 by 2 divided by square root of GME. This is also equal to 2 pi r power 3 by 2 square root of GRE square. GRE square. Time period can also be expressed as 2 pi into r is RE plus h the whole power 3 by 2 divided by square root of GRE square. This is the expression to calculate the time period of a geostationary satellite. For geostationary. For geostationary satellites, the period of revolution must be calculated using this expression T equals 2 pi into RE plus h the whole power 3 by 2 by square root of GRE square. If you look at this expression, time period is directly proportional to r power 3 by 2. If 2 is taken, or 1 by 2 is taken along this side, then it will become T square is directly proportional to r cube. Kepler's third law is satisfied. Kepler's third law is satisfied. So T equals 2 pi into RE plus h the whole power 3 by 2 into square root of GRE square is the expression for geostationary satellite. If the satellite is said to be revolving around the Earth, very close to the surface of Earth, where height is very, very small, then what will happen? The expression will be totally changing here. If the satellite is revolving very close to the surface of Earth, then the time period of the satellite will be given by the expression T equals 2 pi into square root of RE divided by G, which is 84.6 minutes, approximately 1.4 hours. 1.4 hours. This is the time taken by the satellite to revolve around the Earth in circular orbits very close to the surface of the Earth. Even you can calculate the value of orbital velocity with this expression VO equals square root of G into RE. This orbital velocity is 8 km per second. Orbital velocity is 8 km per second by substituting the value of G and R. Right? We will get the value of VO as 8 km per second. Fine. This is about orbital velocity, and this one is about the time period of revolution of the satellite around the Earth. Now, we can speak about the kinetic energy, potential energy and total energy possessed by the satellites which are revolving around the Earth's surface. Kinetic energy is simply given by the expression half mv naught square. Satellite. The kinetic energy of the satellite is given by the expression half mv naught square, where v naught is the orbital velocity. For v naught we can substitute as square root of gme divided by re. V naught square is gme divided by re. Or otherwise, if you speak about the revolution of the satellite at a height h above the surface of Earth, then we can go for the orbital velocity of the satellite as v equals square root of gme divided by small r. This will be applicable for all cases. So we can write half of m into, instead of v square, I can write gme divided by r. So gme small m divided by 2r will give you the expression for kinetic energy, which is always positive. Potential energy of the satellite is given by the expression minus of gme small m divided by small r. gme small m divided by small r. This will give you the potential energy. Then total energy of the satellite can be given as minus of gme m divided by 2r. gme m divided by 2r. If you just look at these three energy scales, or energy values, we can write here kinetic energy and total energy are equal but negative. The negative of total energy will be kinetic energy, which is positive. So kinetic energy is negative of total energy, or total energy is negative of kinetic energy, both are same. Then potential energy is twice total energy minus of twice kinetic energy. While speaking about total energy and potential energy is twice total energy, because total energy is already negative. When multiplied by 2 will give you potential energy. So potential energy is twice total energy and is also equal to minus of twice kinetic energy. So in these cases, kinetic energy is always positive. Potential energy and total energy are always negative. We can draw a graph by taking distance and energy scales. Kinetic energy is taken along this direction, positive. Potential energy and total energy are on the negative scales, just negative. As R increases, kinetic energy decreases. As R increases, kinetic energy decreases. As R increases, total energy increases. Potential energy also increases. This is kinetic energy, this is total energy, and this one is potential energy, can represent as U. So when R is less, potential energy and total energy are less because they are on the negative scale. As R increases, total energy increases, potential energy increases, kinetic energy decreases. Right? From this we can easily understand how the energy values are changing with respect to distance. Right? Up to this, the content of gravitation is over. We can see some examples related to all the formulas what we have discussed so far. Right?